So today we're going to talk about frequency domain. And we're going to give a overview first of all the different frequency domain methods. And then we're going to focus in on one particular. We're going to focus in on the DTFT. That stands for the discrete time Fourier transform. As a warning, don't get behind on these next couple of lessons. Students who have gotten behind on the early part to the frequency domain stuff with DTFT have a really hard time recovering. We're going to cover it from an intuition base first. Then we'll talk about it from a math-based. We'll talk about convergence, because Mitra in the book gives a lot of time to convergence issues. And then we'll talk about some examples. So let's begin with talking about the frequency domain overview. So what we're talking about here is an overview of the techniques we're going to be using for the entire rest of the semester. And I think it's easiest to talk about how the chapters work. We just had one chapter so far, chapter 2, which was all about time domain techniques. But frequency domain techniques are more complicated. So we're going to talk about signals in the frequency domain. And that's going to be in chapter 3. And then we'll talk about systems in the frequency domain. And that's going to be in chapter 4. So chapter 3 is going to be an awful lot about x of n's, y of n's. And chapter 4 is going to be about the relationship between those two and h of n's. I want to first remind you about how this worked in EE430, because it's been a long time for some of you. In EE430, we talked about Laplace transforms. And you'll recall that that worked for any input that had a u of t in it. And the formula for it was the integral of our input function times e to the minus st dt. And then in signals and systems, so you can kind of see what we're doing here. We're moving from continuous time to discrete time. And then in signals and systems, our next thing we talked about was Fourier series. How to break up your any input waveform, any periodic waveform, into a bunch of sines and cosines added together, or cosines with a magnitude and angle that were added together. And then the last one we talked about was sums of complex exponentials, which we said is the integral over any time period t of our function times e to the minus j omega k t all over the time period, where that k is this k, and obviously there's a dt after each of these. And Laplace transforms, we said it had this s in it, and the s didn't really have any kind of intuitive meaning. It was just an s that we had to add so that we could then do the same thing. We could convert the system into a function of s, the system transfer function, multiply them together to find the output as a function of s. Still has this weird s term. It doesn't mean anything intuitively. But then we do the inverse Laplace transform, and it all makes sense now that we've got a y of t. Fourier series had an intuitive piece. You could break the c sub k into the real part was equal to a cosine piece, the imaginary part was equal to a sine piece, and you could see how they added together. And then last, we went back to the Fourier transform, which works for any x of t, left-sided or right-sided, unlike Laplace. And we said that that was equal to the integral of the function times e to the minus j omega t dt. And it actually is what our Fourier series turns into as we let the time period go to infinity. And that works for any x of t. So we covered them in this order in signals and systems. In discrete time, the discrete time version of the Fourier transform is called the discrete time Fourier transform. And it's never spelled out. It's almost always written instead as DTFT. The DTFT works for any input signal, x of n, of course it's discrete, and it's defined to be the sum of x of n e to the minus j omega n. And this is what we're going to learn today. This is a discrete input, but it's a continuous output. Of course, since it's continuous output, it's in frequency, but omega is only unique between 0 to pi. Then the Fourier series is like the discrete Fourier transform. Now hold it. Doesn't that sound exactly like the discrete time Fourier transform? You're saying these are two totally different things? Yeah, they're two different things. I wouldn't say they're totally different, but it's like a finite length DTFT. We'll talk more about that. And then the last is the equivalent of Laplace transforms, and we call that the Z transform. And the Z transform also works for any x of n, u of n, any right-sided thing. And we'll talk about how it's defined, but it's x of z. It looks an awful lot like the x of s. It would have made sense to call x of s the S transform and x of z the Z transform, except we like to celebrate Laplace, who came up with it, like we like to celebrate Fourier and the Fourier transform. Okay, so in big picture, these are the three types of frequency domain methods we're going to use, and we're going to introduce them in this order. First, the DTFT. Second, the DFT, and then last, the Z transform. So in the opposite order that we introduced them in signals and systems. And we do it this way because we're going from the most intuitive to the least intuitive in signal processing, in digital signal processing. So questions about the big picture with what we're doing here?